Hi, welcome to the CIDCI online salon series. I'm Margie O'Driscoll, and on behalf of the CIDCI Board of Directors, I'd like to welcome you here this morning or evening, depending on your time zone. CIDCI's mission is to accelerate change in the built environment by convening innovators for educational programs. We also serve as a trusted source of information about innovation. Special thanks to our sponsors who make all this possible. Before we begin, we want to acknowledge what a difficult time it is for many of you who now juggle homeschooling or home camping, caring for elders, and your day job, all from your home, maybe from your dining room table, just like me. It's a lot. We urge you to be compassionate with yourself, as well as those you live and work with. Today, we have two speakers. We'd like to welcome Tom Machinchick, who spent the last decade as a research analyst, principal research analyst, and consultant in the global commercial and residential buildings technology industry, working with leading firms such as Pike Research, Navigant Consulting, and Manifest Mind. Tom joins us today from his home in Pennsylvania. We would also like to welcome Jack Laken. Focused on integrated building solutions that drive simplification, Jack has over 30 years experience de-risking construction projects in North America. His current expertise with smart city, resilient, zero net energy buildings offer a strategic pivot in carbon neutral buildings. Jack joins us from Toronto. Tom, I think you're going to get us started.
Sam, thanks very much for the introduction, Margie. I'm really happy to be presenting today. We feel we have a unique solution for the sustainable buildings construction industry. And without further ado, I'd like to get started. So as an introduction, today we'll talk about a unique integrated ventilation design that uses the concrete structure of a building to make a building more efficient, sustainable, and resilient while preparing the building for the challenges posed by net zero and net positive buildings, as well as grid-connected smart city initiatives. Now, before we move on, let me just explain that this is not a new technology. So before you hang up and say we're not interested in listening to this, I'd just like to say that we have a 15-year track record of implementing this technology or this design solution, 35 completed buildings, over 2.1 million square feet, 4 LEED certified buildings. We've won a number of awards for our buildings. We also have the 2 most best performing schools in Canada, the best performing school in Horry County, South Carolina, which is actually a 675,000 square foot, 5-building campus. These buildings, the 3 schools that I just mentioned, have been featured in an NREL, a recent NREL report on guide to net zero, zero energy and zero energy ready K-12 schools. And we've also been featured in the Sustainable Schools Initiative in Canada, which actually rated the schools that we built there and achieved that honor of being the most efficient. Our energy use intensity figures are well below the United States DOE building type averages for various ASHRAE zones. So talk about something that is new technology. We have a long history and performance independent audits to back up what we're going to tell you today. But before we go further with the integrated ventilation design, I just wanted to talk about some of the evolution of building technologies in the construction industry, as well as some of the important initiatives that are driving building construction today. So about 10 or 15 years ago, efficiency initiatives were focused mainly on individual pieces of equipment. So if you had a piece of equipment in a building, the manufacturer's desire and drive at the time was to make these individual components more efficient in their operations. That migrated to a systems approach where cohesive management strategies were developed across systems for building-wide optimization. Once building optimization occurred, we moved to a platform type of methodology where facilities have become business assets. They're integrated across the business unit itself and across portfolios and campuses. And with that, that's migrating to connectivity to the grid and smart city initiatives. Smart cities are composed of smart connected buildings. Smart buildings need to be resilient, reliable, efficient, connected, and responsive. But at the same time, you must take into consideration building safety, building comfort, building health, and also think about services for the occupants and tenants of a building, whether that's a commercial building or a residential type of building. The efficiency of the building, the tenant considerations and occupant considerations have to also be taken into consideration, the key component of all of this. Some of the key sustainability initiatives in the construction industry today include zero net electrical energy, zero net energy, zero net carbon. I'm not going to go into detail about what these are. There's a brief definition underneath these subtitles here on the slide. But they're very, very important. I'm sure anybody that's involved in the buildings industry today understands what these are. They're very, very critical, and more buildings are being constructed with these initiatives in mind. Two other important characteristics or initiatives in buildings are embodied carbon. That's the manufacture, transportation, and installation of construction materials, how much carbon is used to manufacture, transport, and install pieces of equipment. And also operational carbon, which is the building carbon-based energy consumption. So without going into these any deeper, just wanted to make you aware that these are key initiatives in the industry, and integrated ventilation design answers most of the questions that these initiatives require. So if we look at a typical building design process, it generally starts with a standard building structure. And then the process evolves into the addition of equipment and other components in the building to make it more efficient. These include HVAC systems, dedicated outdoor air systems, chilled beams, ice storage, sensors, and also radiant in-floor heating. So these systems really work very, very well. They've been tested over time, but it also adds complexity to the building and also adds cost to the building. Oh, before I move on to the next slide, this methodology largely ignores or doesn't address the structure of the building. And if you can see on the left, this is basically the structure of a building made of concrete. There's immense thermal value locked into the structure, especially if it's a concrete building. And with this typical design process, the structure and the thermal benefits that can be attained with this structure are largely ignored. So what is the value of accessing the thermal qualities of the structure of a building? Well, if you can see in this graphic that concrete is far and above many other of the common building materials that are used in the industry today, except for stone, but concrete is very, very easy to work with. So the thermal storage potential of these materials, concrete doesn't even come close, or other materials don't even come close to the thermal value that concrete can bring to the structure of a building as far as a ventilation system is concerned. Concrete also provides extreme weather safety, radiant comfort, higher air quality, very deep efficiencies if used and actively managed, and building resilience, which are all important in the construction of a building today. An integrated ventilation design, you can use the same building process. You have a building with a standard structure. However, you don't need to add on the ancillary, costly, and more complex systems to have the same performing building at a lower cost. So in general, if you have an integrated ventilation design, you still have an HVAC system, but it's reduced by up to 40 or 50% in size. These systems are not necessary, but you'll have a better baseline building that performs equal to or better than for less cost than a building that has this structure with all of these pieces of equipment added. So the benefits of active thermal management, everybody I'm sure is aware of the passive thermal benefits of the concrete in a building. So if sunlight comes through a window and shines on the floor, there's a heat gain in the floor that can actually be filtered into the building or seeps into the temperature of the building at night. So that provides a benefit, but it's a very small benefit. But if you're actively accessing these thermal quality, it unlocks tremendous opportunities for cost savings, comfort, energy efficiency, and also carbon reductions. So instead of your building structure being a large cost center, in fact, it's probably the largest cost of the building itself, you turn that structure into a smart asset versus just a capital expenditure. So this is a little bit more detail. We saw a picture on the first slide as far as an introduction. I just wanted to introduce you to exactly what we're talking about when we say integrated ventilation design. The picture or the graph to the right shows a standard hollow core concrete slab. These are manufactured all around the world, generally within a building, just because transporting them would be too costly to transport them any further. They can actually also be manufactured on site. So what an integrated ventilation design does is it takes a standard hollow core slab and modifies it to actually make it part of the ventilation system. So you have an input duct coming into the concrete slab where a hole is drilled. The air travels through the raceways that are made here and exits into the room or the building through a standard diffuser. The temperature of the air, whether it's hotter in the summer or cooler in the winter, comes through the concrete hollow core slab and is conditioned before it enters the room. On the left, you see an actual picture. This duct here is the main or one of the main HVAC ducts. And you can see these small L joints that are connecting to the concrete slab to form the duct in the slab itself. Jack, is there anything that you'd like to add in talking about this slide?
All right. Well, the slide itself shows that we're turning really a dormant asset into a smart floor kit. That it's not only the ventilation that is going through the structure, but we pick up the difference in temperature, so we can better manage the indoor and outdoor environments. And in fact, this type of approach allows many buildings to be in a natural state, just using ventilation air without any supplementary heating or cooling when the temperatures rise quite a bit above the desired set point.
Okay, thanks, Jack. So what does an integrated ventilation system buy you? With a standard building versus, or when you compare a standard building to a building that has integrated ventilation design, you're actually saving from $10 to $50 per square foot. And this savings comes from the reduction in size of the HVAC system itself, the elimination of a large amount of ducting, such as perimeter ducting that is required in a standard building to assure that the outside temperatures don't seep into through the building envelope into the indoor environment. With regard to life cycle costs, integrated ventilation design is 40% less expensive over the life of a building. You'll notice in the center graphic here, we have a BOMA OPEX factor of 3.0 for a standard building. And what that means is if your building costs $100 million, over the life of the building, you'll spend $300 million on operating expenses. With an integrated ventilation design, the BOMA OPEX factor is 1.8, which is 40% less than a standard building. That means that a $100 million building will have $180 million over the life of the building. Energy consumption is reduced from 35 to 50% as a baseline, and the HVAC system can be reduced from 40 to 50% from what would normally be installed inside the standard building. There's also additional built-in benefits that come with this system that actually don't cost any extra. These include increased tenant comfort, increased digital complexity if desired, increased resilience and safety of the building. There's space savings and aesthetics considerations for the architects and engineers and designers of the building. And there's also financial opportunities that the building can take advantage of, and we'll talk about those a little bit later. With regard to tenant comfort, radiant comfort, I'm sure everybody is familiar with hydronic radiant floors. There's a comfort level with radiant systems that is higher than forced air systems. It's just calmer and a nicer feeling within the building. Our system is not a hydronic system. It's an air-based radiant heating and air conditioning system. We'll get into the details of that in coming slides, but just wanted to let everybody know that there is a difference between hydronic radiant system and a non-hydronic air-based air conditioning and heating system. Most of the year, integrated ventilation design actually operates as a dedicated outdoor air system. So we're using outside fresh air, pulling it through the ventilation system and through the concrete slabs to bring fresh air into the building most of the time. There's actually buildings that we've had that have only used their air conditioning or heating systems during the coldest and hottest weeks of the summer. For the rest of the year, they're basically just using outside in through the system and maintaining indoor comfort levels with higher quality fresh air. And the difference is tremendous when you walk in a building with integrated ventilation design versus a system that actually recirculates stale air throughout the building. There's less noise because the velocity of the air coming from the vents is lower. Cold and warm calls are virtually eliminated because the drift in temperatures within the building, which we'll see in coming slides, is very slow and mild compared to a normal system. And there's also aesthetics, pleasing aesthetics that we'll talk about when we talk about the engineers and the designers in just a couple of seconds here. This system actually reduces complexity because we're reducing the size of the HVAC system. So the HVAC system is smaller, meaning parts cost less, and there's less knowledge that you have to have working on this type of system than with a complex digital system. So you don't need all of the equipment from a few slides ago, like dedicated outdoor air systems as an individual component, ice storage and things like that. You don't have to train up your maintenance personnel to learn how to work with these systems and other digital software systems. You can basically have a lower maintenance headcount and also require less training for the maintenance staff if necessary. If you want a more efficient building, energy conservation measure stacking can take place. So you can use these more complex ECMs if you desire. Your baseline building will just become more and more efficient the more equipment you add. So it's really a choice and a decision that needs to be made for the building itself. With an integrated ventilation system, building resiliency and safety is increased. The fact that temperatures drift slowly means that this building can actually be considered, or a building with integrated ventilation design can be considered for an emergency shelter. For up to 3 days, comfort levels can be maintained within the building without really turning on expensive chillers and other high energy consuming pieces of equipment. Brownouts and blackouts become more prevalent, and this won't disrupt the comfort of the building during these events if they happen during the day. So your work and your home life will remain more stable if you're working in this type of building. And one of the most important things we could talk about, especially during these times with the COVID crisis around the world today, is that communicable diseases will be spread less in integrated ventilation design because of the fact that we're using and bringing in outdoor air most of the time throughout the day. Recirculation only occurs infrequently, and that is one of the major causes of spread of disease, the sick building syndrome and things like that. So this is very important, not only for residents who want to remain safe in their homes, but also for buildings like schools and healthcare facilities where the spread of diseases can really get the whole building sick, even the healthcare workers themselves. And we've heard many stories in the news in recent times. So for the designers, architects, and engineers of the buildings, there's space savings up to 7 to 13%. This means is with the concrete hollow core flooring slabs being used as part of the ventilation, drop ceilings are not necessary anymore. So you can lower the height of the floors, but still have the same height of the ceiling if desired. What this means in, say, like a 60-story building, instead of having 60 stories, you can add maybe 64 or 65 floors to that same height, which brings additional rents, additional office space, additional apartments or condos to the building for the same height. So it's an efficiency in the building process as well. Higher ceilings can be had, and that's a design option. It's a better aesthetic for the people that are in the building. It's also provides options for the architects to do some designs that they prefer within the building. And there's also less ducting to worry about along the perimeter of the building. So you can have taller windows and various things like that. So it provides design options as well as efficiency and comfort options. And finally, some of the financial benefits that we'll see, integrated ventilation design can take advantage of opportunities from, say, utility incentive programs such as demand response, energy efficiency credits, and also time of use pricing. So if we're going over this design process once again, if you remember from the other slide, this is just a different way of speaking about that same process. Generally, a standard building starts over here on the left. We have a column of ranges of energy use intensity, and this is one of the main measures of building designers and engineers today is how efficient is my building, and that is basically measured in energy use intensity. These numbers over here are kBTUs, which is 1,000 BTUs per square foot. So a standard building starts from 40 kBTUs to 80 plus, and these can even go into the of kBTUs in certain climate zones. Once this standard structure is designed, then they work on the building envelope, adding insulation, more efficient windows, a simple HVAC system. That brings the energy use intensity down a notch. And I'm not using specific numbers. These aren't based on anything specific. These are just for example purposes. Once that is done, they move, or they can move, to high-performing HVAC systems and lighting systems. And then we move down further to energy management systems, sensors, digital energy measures, and other things. Once the standard building is brought down to an EUI, an energy use intensity that is acceptable for the building, renewable energy sources such as solar are added to bring the building down to net zero. And if you add even a little bit more renewable energy, you can have a net positive building. So the main point of this slide is a standard building starts here and goes through the process of adding costly and more complex equipment, whereas an integrated ventilation baseline building starts in this range from 20 to, say, 35 kBTU per square foot, depending once again on the climate zone. So for less money, your building will be more efficient. If you want to still go through this process of systems such as ice storage and DOAS and various pieces like that, your building may get closer to net zero, and you'll have to add less renewables to get it to net zero. So there's a cost savings in the renewable energy component as well. This is another slide that shows on the bottom right, you've seen this picture of the hollow core slab and how it connects to basically a standard air conditioner that has been downsized, or HVAC system that has been downsized. The important figure here on this slide is the picture to the left, where you see a hallway in a building where the concrete flooring slabs create the ceiling and the floor in this space. The concrete slabs are connected to the HVAC system. It runs through the concrete slab and comes out into the building. So this gives you an idea of the construction aspect of it. One thing that I'd like to point out is that the air can also come from the floor upward into the building as a displacement ventilation type of system. So ventilation can go upward or it can come downward depending on the preference for the architects, engineers, and the designers of the building.
In principle, the structure basically starts to work in a multitasking mode, which is in contrast to the way mechanical systems in a building operate. They just respond to, let's say, the rise in temperature or a decrease in temperature. You know, the ventilation fan, in fact, is harnessing a lot of free energy, or from the inside bringing out, from the outside bringing inside, or from inside actually moving back into the structure through the return air system. So the system is altogether a lot more intuitive and naturally responds to the outdoor-indoor conditions, but with the key focus on the comfort, which is set, which is user adjustable. So that basically, I guess, that's all, you know, we can add in here.
I think this next slide will complement exactly what you just said. So these are two diagrams from actual buildings. On the left is a conventional building, and what you can see is that during the daytime, which is the most expensive time of the day in certain areas to use electricity, you have the heating system turning on and off, on and off, on and off throughout the day. At the top here, you can see the temperature, the graph of the temperature in the building, where there's peaks and valleys, and this can be uncomfortable for a tenant or an occupant of the building. So during the most expensive time of the day, you have significant variations in the use of the HVAC system and in the temperature swings within the building. This is an integrated ventilation design building. This is a graph from one day in February where the temperature was 4 degrees Fahrenheit or 4 through 17 degrees Fahrenheit during the course of the day. You'll notice that the heating system did not come on throughout the day, yet in the temperature graph we have up here, the building's temperature still drifted slowly upward throughout the day. And where that comes from is the concrete flooring system is actually absorbing heat from the occupants of the building, from the equipment in the building, and also from the lights in the building. Anything that generates heat, the concrete is absorbing. So it's self-heating building in the wintertime when the air was really significantly cold. One other thing that I needed to mention here is that, you know, during the day when electricity is expensive, none of the major consuming pieces of equipment actually turned on during the day. And this is a common occurrence in buildings that have this type of system installed. I mentioned before, but in many buildings, even in climate zone 7, which is Canada in colder climates, the air conditioning system doesn't even turn on at all throughout most of the year, except for, say, the hottest few weeks of the summer and the coldest few weeks in the winter. So during cooling season, the heat from internal loads is absorbed by the precast concrete slabs. And during the night when it's unoccupied, cool nighttime air, fresh air from outside, is brought through the slab to remove the heat from the day that was absorbed from the people and the event. So pre-cools the slabs for the next day. During heating season, during occupied hours, saw in the graph 2 slides ago, heat from the occupants is absorbed into the building and transferred to the hollow core slabs through just normal radiation. During the nighttime hours, recirculation can take place to take that heat that was gained during the day and building. So without turning on the heating system, we use the heat that was generated in the building naturally to heat the building at night and maintain comfortable temperatures. So generally, as I mentioned, recirculation is only used overnight, is used in the winter when heating is needed in hot climates when night pre-cooling is required. There is also the boost option that we have. So if occupant levels in a room or an area of the building increases dramatically or decreases dramatically, quality temperatures or the temperature quality can be maintained in the building. This is an actual graph from a school in Canada. The darker bars here represent a building that does not have integrated ventilation system. And the light green bars here represent a building on the same campus that was built next to this, the dark bar building. But you can see that the air quality remained below conventional or allowed CO2 levels for the building. So these are basically side-by-side buildings in the same climate zone, temperature, city, region, whatever you want to call it. Different systems, different result in the air quality within the building. So one of the reasons why a radiant air conditioning and heating building is comfortable is people are cooled by the radiant heat transfer from their bodies to adjacent surfaces whose temperatures are held a few degrees cooler than ambient. So the input air comes in low. Actually want to go to the next graph. This is a better illustration of it. So warm air has buoyancy and it allows the air to transport itself higher. So you put the treated air where it comes in low, where the people are located closer to the floor, and you allow the stale air to drift higher and be exited from the room or the space that's being conditioned. With a forced air system, you see that the air comes in high and exits high, as an example. And what you have in the building is a mixing of the air. Now, this is detrimental to not only comfort, but if you remember, we were talking about the safety of the building with regard to diseases and other things being spread, sick building syndrome. This mixing is just not a good quality for the building to have if you want to prevent the spread of disease within the building. This is an example of, or a comparison of a building that has a integrated ventilation system versus one that has perimeter ducting in a normal HVAC conventional ventilation system. You can see that with a conventional system, the building envelope is leaking the inside air to the outside. These types of buildings and that type of ventilation system is very efficient at letting the air get outside, or the heat or the cooling that you're actually paying for to seep outside the building. Whereas in the right-hand graph, you see that the building envelope is not letting the air escape through the walls of the building to the outside, because the conditioned air is stored in the flooring system of the building. So there's no ventilation near the walls that's letting it escape. It's within the building as you know, the source of comfort within the air in the building. And with regard to cost savings and cost reductions of a building, this is just a diagram of a normal or standard condominium room. You can see that this building has ductwork along the outside perimeter to maintain comfortable temperatures in the building. And I'd like to move to the next slide here and show you what happens with an integrated ventilation design. So our ducting moves along this corridor here, corridor wall here with a vent here, but these perimeter ducts can be eliminated. And I'm gonna stop talking for a second and maybe let Jack talk about this a little bit more in detail. He's the engineer and I'm just the voice.
Right. So really simplification takes place in residential application. And equally so, it actually works in institutional settings as well. But we're looking here at the residential application. What is interesting is the research shows that only 1% of buildings in the United States have radiant in-floor heat. Our system delivers radiant comfort in both heating and cooling mode. So instantly the comfort level is elevated, over and above what any apartments and condo buildings represent. On the other hand, the systems are very quiet. When it travels, the air is traveling through the ventilated structure. The mechanical noise is not noticeable. And in fact, typical problems with apartment buildings, actually in the independent research, show 5 distinct problems with the conventional approach. Too hot, too cold, too noisy, not comfortable, and they take up too much space. The apartments, these days getting smaller, but the mechanical space required for them remains pretty well the same. So bulkheads are eliminated, radiant comfort added, but besides the focus on the comfort, safety, and built-in resilience, the indoor air quality is considerably improved, and it promotes a better good night's sleep. People that suffer from arthritis that may not tolerate air conditioning in buildings of our type, they basically do not feel the impact of the air conditioning, or the number of complaints are considerably reduced. So, and that goes besides the improved energy efficiency of the building altogether, because it stays in a natural state most of the year. Mm-hmm. So I guess that's for now, completely fine.
Thanks, Jack. So basically done with the presentation, except for showing you some actual real world results. This graph was done, produced by Intermodal Engineering as part of an independent audit of one of our schools, the Mundy's Bay School in Canada. What an Intermodal did was they listed education buildings in North America, their energy use intensity, and this is not in kBTU per square foot. This is in equivalent kilowatt hours per meter squared. So the numbers are different. These can be converted. I guess we can convert these to kBTUs, but let me just mention these blue bars first. So this is the average of an education building in North America. This is an education building in Canada, the average. This is in secondary schools in Ontario. This is the baseline performance of the. So if you remember the process, the building process that we talked about, this is what the standard building would have produced as far as an original estimate of its energy use intensity. After the design implemented the integrated ventilation design, the models showed that the energy use intensity would drop to 150 equivalent kilowatt hours per meter squared. The actual results of the building came in at 138. Now the difference between the actual and the modeled was because models don't pick up the heat from, they don't model the heat that is coming from the occupants of the building, the equipment and the lighting of the building. And so in the actual results, you see the benefits that brings to the, or the integrated ventilation design captures from the indoor components and people that actually heat the building up. This final bar is the Hyde Park School, which is significantly more efficient than even the Mundy's Bay School at 90.2 equivalent kilowatt hours per meter squared. I believe 138 kilowatt hours per meter squared comes in at 12.8 kBTUs per square foot. So when you're talking about buildings that start at 80 to 90 or 50 to 70, to get it down to 12 without many complex energy conservation measures in climate zone 7 is just a tremendous accomplishment. This is a really efficient building, and it costs less and it doesn't have the complexity that most buildings that need to have to reach these type of performance levels. The next part of the presentation is actual slides. I just have a gallery that I'm going to go through quickly, and then we can move to questions. I don't know if there are any questions that people have asked Margie, but this would probably be the time to maybe start compiling them or even asking them as I speak here. We can refer to these pictures if people have questions about the implementation and point out, you know, anything that they might have questions on. So the left picture here shows a completed system with the exposed ducting. Once again, this is the main duct here, and these little L ducts connect the concrete hollow core slabs with the diffuser coming out of the concrete into the room. This is a non-finished building, just showing the raw construction with a rectangular ducting system. This is another picture with a round ducting system, unfinished. Several more pictures. You've seen this already twice in the presentation, which once again shows the duct with the connection to the hollow core concrete slabs. This is a finished system on the left in a school building. This shows the picture on the top right shows a displacement ventilation where the diffusers are on the floor, pushing air from the bottom and exhausting through the ceiling area. And this is another picture of just the end point of a ducting system in a certain building. I'm just going to move quickly through these. All of these just basically look the same. These are some things. This is in a healthcare setting. The picture on the right is blown up. I just want to note that the ducting system moves through the hallway in this office setting, but you can see that this desk here enjoys the benefits of a higher ceiling and no need for ducting along the perimeter of the wall of the building. Jack, if you have anything to interject as I'm scrolling through these pictures, just please jump right in. These are some other spaces. We had interest from a builder in the New York area that wanted to have higher ceilings in a common area. So we put these pictures together for them, but we do, large spaces, small spaces, residential, commercial, office. It doesn't really matter. What building is this a university building here, Jack, on the right?
Yes, that's the High Technology University building in Windsor, Ontario, just across the river from Detroit.
Okay. Just more pictures. This is a picture in a library. So there are certain types of buildings that benefit from this type of system with the less noise requirements and just the higher comfort levels. Schools, you'll have greater productivity of your students. In an office setting, it's noted that if you have good comfort levels, you'll have higher productivity for your workers. In libraries, music rooms, and theaters, you won't have the noise of the ventilation system interrupting your studies, your work, or your performances. And I'm not sure what else to say other than thank you for attending the webinar.
Tom and Jack, thank you so much. That was wonderful. Hey, I have a question for you.
Sure.
What have been the primary obstacles towards use of this system, particularly in the United States?
So the primary obstacle is really lack of awareness. On the other hand, you see the application process is focused more on selecting the best materials, let's say for the building envelope, the best flooring systems. So the fact that we can add smarts to a dormant asset like the concrete floor that all of a sudden eliminates the need for cost and complexity, it's not something that people are aware of, and it's simply the question of awareness. And then once we actually look at any benchmarks that let's say are critical right now, like for example the embodied carbon and operational carbon, by virtue of the fact that we are removing so many mechanical moving parts that are no longer needed. Right there, the embodied carbon footprint is smaller, and the fact we don't need to service them or replace them during the lifetime of the building, that actually reduces the operational carbon footprint. So the value, let's say, of the concrete compared to other flooring systems, if it just compared one against the other, it's not immediately obvious until, like the kind of awareness that we are driving is brought to the attention of the decision makers and designers.
Yeah, I think one of the things that we also run into, I didn't mean to interrupt you, Jack, is when you say thermal mass, people assume that you mean just heat radiation, sunlight radiation through a window, heating up a floor, the passive element of managing thermal mass in a building. When you actively access it, it is just a tremendous, tremendous benefit to the building. It's
a lot of people, when somebody mentions thermal mass, assume that they have it and that's it, and it will do the job for them. But actually intentionally charging it or intentionally managing, and as I said, adding smarts to the dormant asset totally changes the equation, from like a commodity to a value offering that exceeds in more than one way the outcome.
We have a question here from Larry Booth, which is to all the panelists, which are the hollow core panels acceptable to all permitting agencies, especially those in highly regulated, that's my editorializing, state of California?
Right. You see, we totally understand California is a special place, where, a special place in more than one way. In fact, that particular solution definitely, definitely stand to benefit, because the buildings could be heated and cooled naturally most of the time because of the temperature swings. However, to the point of regulations, you see, we complied to the, latest ASHRAE ventilation requirements, whatever they are, and they keep changing, and they'll probably change again now with the COVID, which is fine. Fire rating, which is fine. Life safety, and the building code requirements. So the fire rating, the life safety, and ventilation requirements are kind of the key components of that. Now we comply with the IBC building code, that's International Building Code, that predominantly used, in United States. Local authorities may have some enhancements, which is also not unusual. Whatever the enhancement or additional requirements are, we happy to take a look and address them before the train has left the station.
So short answer is absolutely comply with all building codes and standards. It's happened in South Carolina and throughout Canada. The simple software basically uses standard building controls, is designed just to comply with any of the ASHRAE codes and local codes. So the building operates under the assumption that, we have these codes to comply with, and that's how the software drives it. Is that correct, Jack?
Absolutely. You see, so just to rehash the key points. Fire rating, it's critical. Let's say if there is a 1 hour or 2 hour or higher than 2 hour fire separation between the floors are required, we comply. Ventilation, whatever the latest ASHRAE requirement is there. And the building code, we comply as well. Again, local authorities may have some special requirements, but they, once we know what they are looking for, I'm confident we can address it.
Is there any smoke or fire control techniques required or recommended?
Not any different than the building and the fire code requires. So whatever the fire code requirements are, let's say vertical separations, horizontal separations between different zones, between different occupancy types, that is fairly standard. So that does not have any impact, whatever the standard design is, or the standard requirements to comply. There is no difference.
And it doesn't look like we have any other questions for you. So thank you so much to Tom and Jack.
We really appreciate you letting us speak today. We'd love to get more knowledge about this system into the buildings industry. We really think we can make a difference in sustainable buildings, in the United States, Canada. As Jack mentioned, in areas like California, you don't really even need to place an HVAC system on top of your building. Obviously, that would probably be required by some kind of code or something, but if it came down to it, you don't really need that type of system on your building. In certain climate zones, you could basically run with outdoor air most of the year long.
Yeah, a really fantastic idea. I'm really excited that we got to listen to you guys today sharing this. So with that, I will wrap up. Thank you to our sponsors. I hope you guys have a wonderful rest of your day.
Thank you so much.
Thank you very much. Take care. Bye.